What's up, my stat stars? Michael Princhak here, ready to talk to you about the top 5 things that you need to know about the binomial distribution. Now, this is a pretty tricky topic for a lot of students because it involves probability, but hopefully after watching this video, it's going to be really simple for you. Now, to best explain these top 5 things, we kind of need an example to walk through during this video to kind of tie it all together and have all of these things I'm going to talk to you about make complete sense. So here it is. David is an avid dart player. He's not great, he's not terrible, but over his many years of playing darts, David knows that he has a 13% chance on any throw of hitting that bullseye. So if he has 7 throws of his dart, we can ask 2 questions. How many of those throws are going to hit the bullseye? And what is the probability of each of those outcomes? So now let's dive into the top 5 things you need to know based on this scenario. Alright, the first tip is, well, you need to know exactly what the binomial distribution is. It is a very specific, discrete random variable that is based on 4 pretty specific rules, conditions, requirements, whatever you want to call them. And if any one of these 4 rules fail, well then you certainly can't use the binomial distribution to model your problem. Now, the first rule is that each trial or each time that you do your random process, there can only be 2 outcomes, success or fail. Now, we don't mean good or bad here. We just simply mean success in terms of, what do we want to happen or what are we looking to happen? And fail is, well, everything else, the opposite of success. Now, the second rule is that the probability of success must be given to you and it must stay consistent from trial to trial. The probability cannot go up or it cannot go down, and it's certainly not a conditional probability. Well, if it's in a dark room, David has a 13% chance of hitting the bullseye, but if it's in a pretty well lit room, then he has a 20% chance. No, it can't be any conditional stuff like that. It has to stay 13% no matter what. Now, in generically speaking terms, P is the probability of success, which again, you will be given in a problem. And then 1 minus P, just simply the opposite of it, would be the probability of failure. Now, the third condition is that each trial must be independent of the next, which means what happens on the first trial does not impact the second, or the third, or the fourth does not impact the third, or the 6th does not impact the third, or the third does not impact the 7th. You get the idea. Every trial is independent of the next. And the fourth and final rule, condition requirement, is that you have to be given 2 things. You must be given a set number of trials, and you're looking for how many of those trials you could be successful in. So you got to be given N, the number of trials, and you got to be given the probability of success to have that success in any one of those trials. Now, all of those rules, all of those conditions can all kind of be summarized into one big, giant, beautiful definition of the binomial distribution. A random variable x that counts the number of successes in n independent trials, each having 2 possible outcomes, success or fail, with a probability of success being p and failure being 1 minus p. That's it. That is how we could define the binomial distribution. Again, it's a very special discrete random variable that meets all of these qualifications. Now, let's talk about our problem and how our problem actually does contain all of these rules. First, we were told in our problem that 13% is the chance that David hits that bullseye, and we were told that he's going to get 7 attempts at trying to make the bullseye, and we're looking for how many of those attempts are going to be successful. Now, the first rule is that each throw of the dart is either going to hit the bullseye or it's not. Success hits the bullseye, fail, it doesn't. And the probability of it hitting the bullseye was given to us as 13%, and it cannot change, as I mentioned earlier. Now, again, we also have to have independence, so if David hits 2 bullseyes in a row, that doesn't mean that the next outcome is going to be affected because of that. It's not going to be higher, it's not going to be lower. Every trial is independent no matter what. And then finally, in this problem, we were given a set number of throws, in this case 7, and in those 7 throws, we're looking for how many of them are going to be successful. So all of our conditions are met, so we can successfully model this problem with a binomial distribution. Alright, the next thing you need to know is how to calculate probabilities within the binomial distribution. Now, there is a formula to help you understand how to calculate the probabilities of any specific outcome in a binomial distribution, and here is that formula. Now, this formula is given to you on the AP Stats exam, and I would assume most teachers are going to let you use this formula on a test in class, especially because it is on the formula sheet. Now, at first glance, this formula can, well, be a little bit overwhelming, a little bit confusing, like, what are all of these things? Well, let me try to explain to you very, very slowly here. First, x, the little x, is the number of outcomes you're looking for to be successful, and n is how many total trials you have. P is the probability of success, and 1 minus P is the probability of failure. So the four variables in the equation are actually not that difficult to understand. P, success, 1 minus P, probability of failure. Little x is the number of successes you're looking to happen, and N is your total number of trials. Now, each of these four parts are really, really important. The first part, the n choose x, that's that funky looking n over x in parentheses, that's simply going to tell you how many different ways you can have x successes in n trials. P raised to the x is representing your x successes, because that's what you're looking for, and then you have to have every trial accounted for, so yes, you have x successes, but that means all of the other trials were failures. That would be the difference between the number of trials and your successes. So if you have x successes, then you have n minus x failures. That's why we have the 1 minus p to the x, or 1 minus p raised to the n minus x, excuse me. Now, if you're just like, okay, this formula is still overwhelming, what's going to really make it easy if you actually see me using it in a specific problem. So let's take a look at our problem, and we were looking again at David throwing his darts. Now, let's say we're looking for the probability that David shoots or throws 7 darts and makes exactly 3 of them. Alright, so now I'm just going to fill everything in here. So n is 7, that's how many darts he's going to throw. I'm looking for him to make 3 bullseyes, so that's the 3, or that's my little x. And then the probability of success, remember we said was 13%, and the probability of failure would be 1 minus 0.13 or 0.87, 87% chance he does not hit the bullseye. Alright, now, putting all of those numbers into the formula, we get 7 choose 3. That's that 7 over 3 in the giant parentheses. Then we have 0.13 to the third because we need 3 successes. And then that means we have 4 failures. Because if you got 7 shots, 3 makes, then the other 4 are going to be failures, 0.87 to the fourth. Now, the one tricky thing is, what is this 7 choose 3? Well, this is needed because of the different combinations that we could have 3 bullseyes out of 7 shots. The idea is that it doesn't matter which 3 of the trials he makes the bullseyes on, it just has to be 3 of them. For example, it could be the first 3, make, and then miss the bullseye, miss the bullseye, miss the bullseye, miss the bullseye. Or he can make the first bullseye, not make it, not make it, not make it, then make it on the 5th, not make it on the 6th, make it on the 7th. Or even another example is that he doesn't make on the 1st, makes on the 2nd and the 3rd, doesn't make the 4th or 5th, does make the bullseye on the 6th, and then doesn't on the last one. Again, there's actually more combinations here. These are just 3 of them, but the point is there are lots of different combinations where he has 3 successes, meaning he hits the bullseye, and 4 where he doesn't. Now, how do we actually figure out how many combinations there are? Because the last thing we want to do is sit here and try to list them all. Well, that's where we actually could use this notation of 7 choose 3. Now, there is a mathematical formula to actually do it, or try to do it by hand, but in most cases I just tell students, just use your calculator. Now, how do we calculate 7 choose 3 on our calculator? Well, first off, I'm going to tell you the answer is 35. I mean, that there are 35 different combinations that if you have 7 trials, 3 of them could be successful. How do I get my calculator to tell me that though? Well, first you type in 7. Pretty simple. Then you're going to hit the math button on the left-hand side of your calculator, slide over to PRB, which stands for probability, at the top, and then you're going to choose NCR, that's our combinations. Then you're going to type in a 3. So you typed in the 7 first, then the NCR, then the 3. N is the 7, how many total trials we have. 3 is the number of successes we're looking to happen. And this is going to tell you 35, and there's 35 different combinations. Now the good news is that every one of those 35 combinations has 3 successes and 4 failures. That is why the 0.13 to the third and the 0.87 to the fourth stays the same for every one of those 35 different combinations. So now to finish this off, I just take the 35, times it by the 0.13 to the fourth, 0.13 to the third, times it by the 0.87 to the fourth, and I get 0.0441. So there's about a 4.41% probability that David hits 3 bullseyes in his 7 attempts. So kind of unlikely, not totally out of the question, but on the lower side, that's for sure. Now, if I actually took my time to find all of the probabilities for all of the outcomes, I would get a table that looks something like this. So once again, if David's going to shoot 7 darts, he can make all 7 of them, 6 of them, 5 of them, 4 of them, 3 of them, 2 of them, 1 of them, or he can make none of them. And using that probability formula, I went ahead and found the probability of each of the outcomes. So we see the probability of 3 is exactly what we just walked through, 0.0441. But if I repeated that process for all of the other outcomes, I found the probability of 0 bullseyes is 37.7%, probability of 1 bullseye is 39.5%, all the way up to the probability of 5, 6, 7 bullseyes, which have some very low probabilities. Again, David's not bad at shooting darts, but making a bullseye on any one throw is only 13%, so for him to do it 7 times in a row is going to be, well, very, very unlikely. And this table becomes our probability distribution of all of the outcomes for the random variable and all of the probabilities. Now the third tip, the third thing you need to be able to do with the binomial distribution is calculate probabilities of multiple outcomes. So we just walked through find the probability of exactly that one outcome of 3 bullseyes. But what about if we want to kind of combine some of those probabilities together? For example, we could ask you, what's the probability that he makes more than 2 bullseyes? Or what's the probability he makes less than 3 bullseyes? Or what's the probability he makes at least 1 bullseye, which is greater than or equal to 1? Or what's the probability that he makes at most 5 bullseyes, which would be the probability that he makes less than or equal to 5? Now the first thing we need to know is that you can answer any probability question by calculating the probability of exactly what's asked of you, or you can calculate the probability of what you don't want to find, or what you're not asked. And maybe you're like, hold on, what? What are you talking about? All I'm trying to say is this: when you are asked to find a probability, you could do the work to find that probability. Or you could do the work of not that, which you don't want to happen. But if you're going to go the route of finding the probability of what you don't want, then you just simply have to do 1 minus that probability. That way you can get back to the probability of what you do want. Pretty simple process that I hope you've learned in class. Now, for example, if we're asked to find, hey, what's the probability that x is greater than 2? First, that does not include 2, that's strictly greater than 2. That would be 3 bullseyes, 4 bullseyes, 5 bullseyes, 6 bullseyes, or 7 bullseyes. So all I gotta do is add those probabilities together. It's really that simple. Or another way I could do it is I could find the probability for what I don't want. What I don't want is 2 bullseyes, 1 bullseye, or 0 bullseyes. If I go that route to find the probability of what I don't want, then I'm just going to have to do 1 minus that total probability. So if I have that nice table of all of my outcomes, all my probabilities, I can find this probability 2 ways. I can look at that table and I can add up 3, 4, 5, 6, and 7 and those probabilities, or I can add up 2, 1, and 0. But if I'm going to add up 2, 1, and 0, I got to do 1 minus it. Now, on a FRQ, you do have to show work, so typically students are going to show work that's easier or faster, less steps. So do I want to show the work for 3, 4, 5, 6, and 7, or do I rather show a little bit less work and show 2, 1, and 0? Well, most students are going to choose to show less work. So here's what I would do to find the probability that x is greater than 2. I would do 1 minus the probabilities of 2 bullseyes, 1 bullseyes, or 0 bullseyes. Remember, this is what I don't want to happen. So if I add up those probabilities, and I get 0.9487, then I subtract that from 1, I get 0.0513. That's the probability of what I am looking for. Now, if you want to double check me, just add up the 3, 4, 5, 6, and 7, and it will get 0.0513 as well. But again, you got to show your work, and it's a little bit easier to show less work. All right, so make sure you truly understand how to do that. There's oftentimes going to be an FRQ involving binomial distribution, and just know that the AP test is never going to have you do tons and tons of calculations and really hurt your wrist by writing so much. So if they ask you to find a probability, there's a good chance that there's probably an easier way to do it. For example, another problem might say, what is the probability of at least 1 bullseye? Okay. At least 1 means 1 or more. That's 1 bullseye, or 2, or 3, or 4, or 5, or 6, or 7, and I'm already thinking, I don't want to show all that work. So this is where I would definitely say, well, what about what you don't want. The opposite of at least one is none. So that would only involve one calculation, find the probability of no bullseyes. I could do that very, very easily, and then, because that's what I don't want, I'm going to do 1 minus that. So if I find the probability of no bullseyes, which just takes a couple steps, I get 0.3773, and then I can do 1 minus that to get 0.6227. So the probability that David makes at least one bullseye is about 62.27%. Pretty easy to solve it this way, and way faster, especially when you have to show work. Now my fourth tip is know how to use the calculator to make shortcuts. Alright, there are two commands on the calculator, binomial PDF and binomial CDF. They're going to save you tons of time. Now, on an FRQ, you still got to show work, but using these commands is a great way to check your work. But on a multiple choice question, you actually don't have to show work at all, so using these commands is going to save you a ton of time. First, how do you access these commands on your calculator? Hit second vars. That vars actually stands for variables, but it doesn't matter. Second vars is your list of distributions. Scroll down a little bit and you will see the two commands, binomial PDF and binomial CDF. Let's talk about each of them right now. Now the binomial PDF, this command will calculate the probability of exactly X successes in N trials. This will do the exact value you tell it. So for example, if I wanted to find the probability of 3 bullseyes in 7 trials, I'm just going to go ahead and select the binomial PDF. The number of trials is first, so I'm going to put 7, representing the 7 shots. Then I'm going to put P, the probability of success, 0.13, that's what's told to us. And then the X value is how many successes we want to happen. And in our problem, we wanted to find exactly 3, so I'm going to type a 3 there. Hit enter, and you're going to get your answer of 0.0441 pretty easy. So instead of doing all of this work, all you have to do is this, and you get your answer. So on a multiple choice, that's going to save you tons of time. Now, what does a binomial CDF do? This command will calculate the probability of X successes in N trials and also the outcomes of anything less than that X value. Now, CDF stands for cumulative density function, but what I like to say is it stands for counts down from. So if I use a binomial CDF command and I put a 3 in the X value, it's going to not just do X. It's not going to just do 3. It's going to do 3, 2, 1, and 0 and add them all together for you. It's going to put them all together for you, which is pretty nice. It's going to save you a lot of time for some of those questions that ask you for multiple outcomes at the same time. So if I'm trying to find the probability that he makes 3 or less bullseyes, I'm going to go right to that binomial CDF, 7 trials, probability of success 0.13, and if I type in a 3 there, remember it's going to do 3, 2, 1, and 0, and add them all together for me, and I get 0.9928. Now what about this question? What is the probability that the number of successes is at least 5, meaning 5 greater than or equal to 5? Okay, so I'm thinking, all right, I gotta show my work, so greater than or equal to 5 would be 5, 6, or 7. So I can show the work for 5, 6, or 7. But how can I get this answer really, really quickly using these shortcuts on my calculator? Well, unfortunately, we don't have a command that counts up, we only have a command that counts down. So my thought process is, okay, greater than or equal to 5 means 5, 6, or 7. The opposite of that is 4, 3, 2, 1, or 0. And that's exactly what a binomial CDF can do. So I can use a binomial CDF with a 4, and that's going to automatically combine the probabilities of 4, 3, 2, 1, or 0 outcomes, and then I can hit enter and get my answer. But this, remember, is what I don't want. I don't want 4, 3, 2, 1, or 0. I want 5, 6, or 7. So if I'm going to go this route of finding what I don't want, I just can't forget at the very end, I have to do 1 minus my result. And I'll get the answer. And it's an extremely low probability. Look at that scientific notation there. The probability would be 0.00062. Extremely low probability that he makes 5, 6, or 7 bullseyes. Why? Well, remember, David only makes 13% of his shots into the bullseye, so getting 5, 6, or 7 out of 7 shots probably going to be pretty unlikely. But the commands on your calculator are really awesome. They're very useful if you know how to use them. So use them to your advantage, especially on a multiple choice question where you don't even have to show work. The final tip for I have you is know how to calculate the parameters of a binomial distribution. Now, what are the parameters? Well, we're talking about the mean and the standard deviation of the random variable x. Now, there are formulas for these two values, which is super awesome. They're on the AP Stats formula sheets. Hopefully you've seen these before. The formula to calculate the mean of a binomial distribution is simply n times p. N is your set number of trials, p is your probability of success. And then the formula to calculate the standard deviation is a giant square root, and inside that square root is n times p times 1 minus p, which is the probability of failure. Now, please note that these formulas don't work anytime you're asked to find a mean or standard deviation. They only work if you're finding the mean or standard deviation of a situation that you officially have deemed a binomial distribution or a binomial problem. So please don't blindly use these formulas. Make sure that you are definitely in a binomial distribution before you use them. Now, the next thing we have to know is, what do these two numbers tell us? What do they represent? So first, the mean of a binomial distribution is the average number of successes in n trials that we would expect in the long run. So if we were to repeat our random variable many times, what is the average number of successes we would expect in the long run? Now, for our specific problem, remember we were shooting 7 darts and the probability of making that bullseye was 13%. So the mean would simply be 7, that's n, our number of trials, times the probability of success, 0.13, and we would get 0.91. But what does that 0.91 represent? It means that in 7 throws, or 7 attempts of throwing a dart at a dartboard, on average, David expects to make 0.91 bullseyes. Now, this is all in the long run, right? In any one trial of throwing 7 darts, he's going to make 0, 1, 2, 3, 4, 5, 6, 7. He's never going to make 0.91 bullseye. That doesn't even make sense. That's because this is a mean. So if David were to throw 7 darts, throw 7 darts, throw 7 darts, throw 7 darts, repeatedly throw 7 darts, on average, he would make 0.91 bullseyes in the long run. Now, what about the standard deviation? What does it represent? Well, the standard deviation is simply a measurement of the fact that, yes, we expect the mean, but it might not happen. We might get something more, we might get something less. It's going to vary, and standard deviation is a measurement of variation. Now, the formula for our problem, again, is pretty simple. Giant square root, 7, that's our n, times 0.13, that's our p, times 0.87, that was our probability of failure, and we get 2.108. So, in 7 attempts of throwing a dart, we expect to make 0.91 bullseyes, but that number of bullseyes could easily vary by a little bit more on the top end, a little bit more on the bottom end, and that's what the 2.108 represents, the fact that the number of successes that we're going to have is going to vary in the long run. Every time David has 7 attempts at that dartboard, he's not going to always get the same number. It's going to vary a little bit, and that's exactly what the standard deviation measures for us. Now let's expand this problem that we've been talking about, making it a little bit bigger. Let's just say that David is going to be in a tournament where he's going to end up shooting 600 darts. What is the mean and standard deviation for the number of bullseyes he expects to have over those 600 attempts? Well, pretty simple. The mean is taking 600 times 0.13, so he expects to make 78 bullseyes. Does that mean he will make 78 bullseyes? Absolutely not. It's an average in the long run. So over the course of many trials of 600 darts, 600 darts, 600 darts, in that long run, he expects to make 78 bullseyes on average. But of course, sometimes it could be more, sometimes it could be less, so there's a standard deviation attached to that as well. So we use our standard deviation formula with 600, 0.13, and 0.87, all inside that square root, we get 8.238 as the standard deviation for the number of bullseyes that he'll successfully land in 600 throws. Alright, that's it for the top 5 things that you need to know about the binomial distribution. Overall, it's really not that hard to work with. The one thing that does give kids a lot of headaches is that probability formula. But if you take your time to process what each part of it represents, N is how many trials I have, X is how many of those trials I want to be successful on, it's actually a pretty easy formula to use. You just have to understand how to get that first part, which simply represents how many different combinations you could have of X successes in N trials. Once you get past that, it's actually pretty easy. And I do have a ton of other videos that describe it in a lot more detail if you want to watch. Now, Also, don't forget about those shortcuts in the calculator. They're definitely going to save you lots of time. If you just know how to use those, you could probably get a lot of multiple choice questions correct as well. Alright, hope you enjoyed the top 5 things you need to know about the binomial distribution. Good luck on any future assessments you have over the topic.